In a distributed system, what if one of the nodes wants to efficiently broadcast a message in the network? The situation is not as simple as it sounds because there is no single node that holds the information about the entire topology. All they know is their immediate neighbors. That's it. In this video, we take a look into an algorithm that powers synchronous breadth-first search traversal in a distributed setup, understand its time and communication complexity, and talk about its applications. But before we move forward, I'd like to talk to you about a course on system design that I've been running for over a year now. The course is a cohort-based course, which means I won't be rambling a solution and it will not be a monologue. Instead, a small focused group of 50-60 engineers every cohort will be brainstorming systems and designing it together. This way, we build a solid system and learn from each other's experiences. The course to date is enrolled by 600 plus engineers spanning 9 cohorts and 10 countries. Engineers from companies like Google, Microsoft, GitHub, Slack, Facebook, Tesla, Yelp, Flipkart, Dream11 and many more have taken this course and have some wonderful things to say. The coolest part about the course is the depth we go into and the breadth we cover. We cover topics ranging from real-time text communication for Slack to designing our own toy load balancer to ClickBuzz's live text commentary to doing impressions counting at scale for any advertisement business. In all, we would cover roughly 28 questions and the detailed curriculum split week by week can be found on the course page which is linked in the description down below. So if you are looking to learn system design from the first principles, you will love this course. I have 2 offerings for you. The first one is the live cohort based course which you see on the left side, and the second one is the recorded course which you can see on the right side. The live cohort based course happens every 2 months and it will go on for 8 weeks, while the recorded course contains the recordings from one of the past cohorts as is. If you are in a hurry and want to binge learn system design, I would highly recommend you going for the recorded one. Otherwise, the live cohort is where you can participate and discuss things live with me and the entire cohort and amplify your learnings. The decision is totally up to you. The course details, prerequisites, testimonials can be found on the course page arpitbhayani.me/masterclass, and I would highly recommend you to check that out. I put the link of the course in the description down below. So if you are interested to learn system design, go for it. Check out the link in the description down below, and I hope to see you in my next cohort. So breadth-first search is a very critical algorithm in any distributed system because it powers some of the key features that we need. For example, if you'd want to broadcast a message in a minimum amount of time, breadth-first search comes at play, right? When you'd want to build a topological understanding of your network, breadth-first search comes at play. When you'd want to compute stats about your network, for example, how big your network is, or basically what's the diameter of your network is, then again breadth-first search traversal comes at play. Right? Now this breadth-first search traversal is the algorithm that we'll be discussing is a synchronous algorithm. Now what does this mean? Like you would have heard this term in quite a few videos that I put out, that it's a synchronous algorithm. So here, the key idea of a synchronous algorithm is that every single node of the network participating in the algorithm, they know when to move forward. They are not like they are independent, but they are synchronized to move forward together. And the way they would be achieving synchronization could be pure time-based ticks or maybe some sort of message passing system. We are not going into that implementation detail, but somehow they are synchronized because there are algorithms to achieve that. But if I talk about it, it would be a huge video on its own, but understand this for now, that synchronized, because this is a synchronous algorithm, every single node would be taking its algorithm forward synchronously with other nodes. So they would be moving forward in sync, right? Okay. Now that we discussed, okay, this is the problem statement and this is what we are doing, but what would be the output of our algorithm? So because it's a breadth-first search traversal, the output of this traversal would be a breadth-first directed spanning tree, which means the distributed network, it can very well be a bidirectional network, which means every 2 nodes are connected via bidirectional communication, let's say TCP connection, right? But the output of this algorithm, because what we want to do is, this is not where we stop. Breadth-first search is not where we stop. This is a building block to power a lot of other functionalities, which means that we need to come up with something concrete that would help us build a lot of other systems on top of it. So that is where the output of this algorithm will be a breadth first directed spanning tree. Now what is a spanning tree? Same as our graph algorithm in our typical DSA course. Spanning tree is where you cover all the nodes of the graph but only a limited number of edges, or rather a bare minimum number of edges for you to cover the entire graph. Right? This is what a spanning tree is all about. Right? It may not be a minimum spanning tree, but a spanning tree nodes with edges, with the bare minimum edges that they converge. Right? So just to highlight that point, a node may be reached via multiple nodes, but in a BFA spanning tree, only one of them would be the parent. Right? So this is what is important to understand, because this is what would lay the foundation for a lot of routing based distributed algorithm or traversal based distributed algorithm, where now we are converging on no matter how many edges are there, we would be reaching to every single node with a subset of edges. May not be minimum, may not be maximum, but the number of edges that we would need to cover, we would be keeping it to a bare minimum. Right? It may not be minimum weight when we're talking about it. Let's just be clarifying that. Okay. So now that we know what the input is, what the output is, now in a distributed setup, see how interesting things get. Right? Now let's talk about the algorithm. So because the algorithm is synchronous, right? So every node moves forward step by step, round by round, like they are synchronous in that way. Nodes proceed in sync, and let's say the BFS, the breadth first search, has to be initiated by some node, right? It cannot be like when you are building that topology, you need to know ki, hey, this is the node which is initiating the breadth first search in my network. Now we say that, let's say I0 is the node that initiates the breadth first search, and there are total n nodes in the system. Now the algorithm proceeds round by round. The first round is where I0 sends a search message to its neighbor. Now search is just a general terminology. Implementation, like you just need to create a text message and then send to the nodes, but I'm just classifying that message as a search message, right? So I0 sends a search message to its immediate neighbors, because the only thing that the node knows are their immediate neighbors, nothing else, right? So when a node receives a message, right? When a node receives a message, it first checks that, hey, am I marked? Like, did I receive a search message from someone else before? If I haven't, which means if I am an unmarked node, then I will first mark myself. That, hey, I received something, now I am part of the spanning tree, right? And as soon as I know, okay, hey, I have never received a message beforehand, and this is the first time I'm receiving the message, I am part of this spanning tree, and I'll update my parent. So whenever a node receives a search message, if it is an unmarked node, then it would be marking itself, okay, hey, now I'm part of the spanning tree, and this is the node from which I received the message, so this node becomes my parent. Right? And this is what the first round is going to be. Right? Now, in the second round, the nodes who received the message in the first round, right? Like, for example, if node I0 send message to A, B, and C, now in the second round, A, B, and C would participate. So the idea is, with every round, the nodes who just received the message would participate in the next round. Right? So the nodes who just received a message in the round 1 participates in the round 2, and they send a search message to its outgoing neighbors. And this process repeats until the entire graph is covered. It's easy for me to say, but how do we do? We'll talk about that. Right? So here the receiving node takes action by marking themselves and continuing the process. Eventually every single node will be covered and would be having and would be part of a spanning tree, right? And we would be covering this entire part. We would know for each node which other node is the parent. Although it might be reached via multiple paths, we would know which one of that is the parent, right? Now, if we talk about the complexity analysis of this, given that the nodes proceed every round, the time taken to cover the entire network will be proportional to what? To the farthest, because at each round, the nodes that received the message in the previous round, they participate there, right? So what would be the time taken for me to cover entire network? It would be the maximum distance between any two nodes in the graph. And that is nothing but the diameter of the network. So if the diameter of the network is 5, it would take me 5 rounds to reach that. So the time complexity of this is the diameter of the network, right? And the number of messages that are exchanged, which is the communication complexity, will be what? Will be, because we are sending how many messages in each round? The number of outgoing edges from the nodes participating in them. And once that node participates, they are not re-participating again. So what would happen is the overall messaging, the overall communication complexity, which is the number of messages exchanged, would be equal to the number of edges in the network. So this is the complexity, because this is very different from our traditional graph algorithms on how we measure complexity. In distributed system, we do it with time complexity and communication complexity, right? Now here, when we think about this, hey, chalo, let's say we build this spanning tree. But in most cases, what is happening here up until now is every node knows which node is its parent. But parent should also know which one of the nodes chose it to be the parent. So for example, if I0 sends message to node A, B and C, and let's say A and C were already part of the spanning tree, so B is the one who received the message for the first time and it marked I0 as its parent. So I0 needs to know that B marked itself as the parent. Basically, just having an outgoing edge does not mean that that node is the parent in this distributed breadth first spanning tree, right? So we need to know out of A, B and C, which one chose it. So basically I0 should know, right, who did that. So how do we accomplish it? So here what would happen is, as soon as a node receives the search message, right, if it is marked, like if let's say it is already part of the spanning tree, it would say I will discard the message, right? So node discards the message, and if it is not marked, which means it is receiving the message for the first time, it would update its local state with this as the parent. So if B received the message, it would mark I0 as the parent locally. It's not any broadcast something happening, right? Now, this was the usual flow, but now because I0 wants to know who chose it to be its parent, now what would happen? The node B would need to send a message, to I0 ki, hey, I chose you as my parent. Now, if only B sends the message that, hey, I chose you as a parent, what about A and C? If I0 does not receive message from A and C, because it's distributed system, something could go wrong, it might just wait infinitely for them to receive the message, or it might just assume that the message was never reached there. So that's why we have to be very concrete with the implementation, very robust with the implementation. So what we do is, whenever we send, or whenever a node receives the search message from other node, it would be sending back if it chose the other node as a parent or not. So a parent/non-parent message is sent from all the outgoing nodes to the node from which it received the message, right? So that node would know if it is chosen as a parent or not by the other node. This way, the parent now also knows the information about the child, that hey, these are the nodes in my directed spanning tree, these are the nodes who chose me, right? And this is how you would build you would have your nodes getting to know your child as well as your parent, like all nodes knowing that information, right? Okay, now comes the main part. How would your algorithm terminate? We discussed that it would take diameter number of rounds to reach that. But how would you know, or how would the nodes know that algorithms terminate? Because everyone's working independently. They don't know on what's happening, how deep the network is. They know that something like n nodes exist. That's it. But there is no one node that holds all the information together. This is the beauty and the beast of distributed system, right? And we can't do much about it. So that is why throughout this series you would have seen how much stress are we putting into terminating an algorithm, because that's extremely difficult when we are in a distributed setup. Single machine, it's okay, you can just run a graph algorithm and you know when the process ends. Distributed system, you can't say much. Okay, so this is where the approach that we take for the termination is called as converge cast. We have heard of broadcast, where we broadcast a message. Now converge cast is the opposite of that, where everyone sends the message to one. So it basically all the messages converge to a single node, right? So the core idea, building on the child pointer that we talked about, that a message sent to the outgoing edges, the nodes report if it's parent or non-parent to the incoming node, right? Now here, just a slight twist to that a node responds to its parent only when it receives message from all of its children or all of its outgoing nodes. As simple as that. So we are adding this blocker so that we maintain this synchronicity, that hey, once everyone, you would respond only after you received an acknowledgement from every single of your child. This way you would see it very beautifully converges to the node that originated it. So let's say I sent a message to A, B and C. Let's say B has children D and E. So B would wait for response like parent/non-parent message from D and E. When it receives message from both, then only it would send reply to I0. Right? And this is the idea. This is called as a converged cast in distributed system. You'd say how complicated it is. Like it was so simple. It's not. It's distributed system. Node has no information about what's happening at other node, and which is where you have to rely on message passing. You have to devise these algorithms such that you are not missing out on any case. It looks like extremely small baby steps, but that's how distributed systems are. You have to take those extremely delicate baby steps to ensure that everyone's on the same page. Right? So by adding this blocker, we are ensuring that the outgoing messages percolate, and then a node responds only when it received all the messages or all the responses from its corresponding children, and so on and so forth. This way, the originating node would know ki, hey, this is these are his children, and now the algorithm is complete. And then it would inform key, and then it may again send a message in the network that hey, algorithm is complete and whatnot. But in this case, it does not need to, because it was not a lead relation that you need to announce something. It would just know that algorithm is complete, right? And then it can proceed to other use cases that needs to be built on top of this spanning tree, right? And again, this is called as converge cast, where we are converging back to something. This is an important pattern in a lot of distributed algorithms. Right? Now here, two very interesting cases. First of all, if the network is bidirectional, it would be simple. Like for example, if B sent message to D, if let's say I0 sent message to A, B and C, it's easy that on the same communication line, A, B and C can respond to I0, right? Because the communication line is bidirectional. What if that communication line is unidirectional? Which means that I0 can send message to A, but A cannot respond back to I0. So how would A tell I0? A would initiate another breadth first search to inform this message to I0 via some different port. So in a unidirectional distributed network where the communication line are unidirectional, it would have to trigger, like every node would be triggering another breadth first search to inform its parent. Huge number of messages exchanged, but you have no other way. If the communication line is unidirectional, you have to do this. If it is bidirectional, it can just respond back. Now you see the complexity of distributed system, that you cannot even assume it's a bidirectional line. You have to think about every single use case when we are designing it. And this is the ultimate beauty of distributed system, right? Okay. Final thing to discuss in this video is applications. Applications of synchronous breadth first search traversal. First, efficient broadcast. You would have seen it from farthest of distance that, hey, this is the classic case where I can use this system to broadcast something to my network and I would know that everyone received it. Right. So if a node in a distributed system wants to broadcast a message M, it can just initiate the synchronized BFS algorithm with itself as the root. The message would be propagated to all the children in the tree and they would be responding back, yeah, acknowledging. This traversal very heavily used for broadcast. Second is distributed computation. You saw how converge cast was happening, that a node waits for all of its children to respond. This is a very classic case to power distributed computation. For example, MapReduce. MapReduce is a classic case of this, where you are sending a computation job throughout the network. You are waiting for all the workers to come to compute. Then they send back the result, and then you send back to the user. Right? So distributed computation, if you want to fan out a computation in your distributed network in order to leverage the computational capability of your entire network, this is the way to do. It's a classic post-order traversal. If I talk about in a DSA language, classic post-order traversal. And then, as I said about computing diameter of the network, now what would happen is, let's say I want to compute the diameter of a network, which means that what is the farthest or what is the largest distance between any two nodes in my network. Now, how can we achieve this? Every node initiates a BFS, and thus they would be knowing which node is the farthest from that node, and they would all converge, flood each other with the same message, and they would all know the global maximum of it, and they would know the diameter of the network. Right? So this particular algorithm, breadth first search, it's foundational for so many other things. Right? And these are the challenges that comes in when we are operating in a distributed setup. Like, we cannot even assume anything. It's the bare minimum assumption that we have to move forward with. And I hope you like this. And this is what I wanted to cover when it comes to breadth first search traversal in a distributed setup. Now you see how challenging it can get, how brittle distributed systems are. But yeah, that's the fun part of it, right? Great. So that's it. That's it for this video. If you guys like this video, give this video a thumbs up. If you guys like the channel, give the channel a sub. I post 3 in-depth engineering videos every week, and I'll see you in the next one. Thanks again.